Okay, so quick recap of last time. We got to the idea of conservation of energy, and it says that as long as there are no non-conservative forces like friction, tension, that sort of thing doing work on the system, then the mechanical energy of that system is conserved. You can think of that as your personal money accounts. So you're checking your savings, all that stuff. As long as there aren't things that are paying you money from outside or taking your money away from outside, that's more friction's role in things, then you will keep the same amount of money at all times. You'll keep the same amount of mechanical energy. Then we just applied that to a couple examples to see that it can do some things that Newton's laws can't, or at least can't do easily. So the setup is you just say initial equals final mechanical energy, you split that into kinetic and potential, and then you just kind of see what's zero and what you need to do some algebra with to get your final answer. And that pretty much is the setup for any conservation of energy problem. This section, we started talking about it's sort of a more abstract view of energy, but it also puts a picture to it in a way. So I don't think I set it up very well last time. So I want to try starting not completely over, but just kind of giving a general sense of it, taking a couple steps back. So I'm going to redraw this picture off to the left. This was looking specifically at a spring. This is position. This will be elastic potential energy. And zero here is when you don't stretch the spring. So it's the relaxed position of the spring. If we had a picture of our spring, this would be when it's at the relaxed length. But say I start to stretch it a little bit, it's going to gain some potential energy. If I stretch it even more, it'll gain even more potential energy. If I stretch even more, it gains even more. And so this is sort of a 1D picture still. I'm still just stretching the spring out to the right or to the left. But the potential energy kind of makes it look like there's a hill that I'm climbing up as I stretch this spring. So instead of imagining a spring being stretched, I can sort of imagine lifting a boulder up a hill, like Sisyphus trying to push the boulder up the hill further and further. And if I compress the spring, we see the same trend. I'm building up potential energy by compressing it, going the other way. But I could also imagine that as sort of lifting a boulder up a hill. That's gaining gravitational potential energy, but it's still potential energy. And so this would be my potential energy curve. It's the possibilities I have for the state of the system. What I could actually reach depends on how much energy I put in by doing work on the spring. So that's basically deciding, okay, where do I actually get the boulder up to? Am I pushing hard enough on the spring to get the potential energy to this level, or equivalently to lift the boulder up that high? Or am I doing a little bit more work to get the level up to here? That's my total mechanical energy. That's my budget of energy that I am allowing for this system. How much of that budget is taken up by potential energy and how much is taken up by kinetic is the thing that can vary. So if, say, I got up to this point and I let the boulder go, in other words, released the spring, we see that the spring is going to start to relax, or in other words, the boulder starts to roll back down the hill. And as it does so, it's going to gain kinetic energy. How much kinetic energy? Whatever's left over that's not potential. So here it's going to have that much. As we return towards equilibrium, it gains more kinetic energy, so it's speeding up. At the equilibrium position, I have maximum kinetic energy because there's no potential energy left there. I'm at the bottom of the hill effectively on this potential energy curve. And so I like to think of potential energy curves as a way of turning a problem about any system back into a problem about gravitational potential energy, the one that's probably the easiest to sort of picture, visualize. And that's what I mean when I say no matter what the curve looks like, just picture it as a literal hill. Picture moving through this system as literally a ball rolling down a hill, no matter what the actual system is. All right, so what we had talked about last time was these turning points. That's just essentially if you happen to let the ball go from there, That means you started it off with zero kinetic energy. That's the highest it's going to be able to make it. So like in this picture over here, if I set the mechanical energy at that height, that dotted line, then at this point where the ball reaches that height, I've run out of kinetic energy. It's all potential. Over here, same deal of if this dotted line, the one that's I didn't have to draw in by hand, if it was already there, if I set the budget there, that's all I've got to work with. And so if I release my system from there, whatever it may be, but I could think of it as releasing a boulder from there, it's going to have zero kinetic energy, and on the other side, it will have zero kinetic energy. All it can do is just oscillate back and forth between those two extremes, those two turning points. So that's why we label TP, turning point. All right, so the only thing I can do in order to raise that roof, in order to lift the boulder up higher than this level that I've set, is have an additional input of energy to the system, or remove energy from the system. And that's why I say only non-conservative forces can do that. Friction would tend to lower this. It's the idea of the boulder doesn't make it as high after each cycle back and forth. Or I could input more energy, give the boulder a kick, and that will raise that energy level, my total budget. And that raises also how much is available for the kinetic account at any time. Okay, so that's turning points. Equilibrium points are a slightly different thing, but another thing that's kind of easy to see on the curve. So first, in order to talk about equilibrium points, we need to remember what equilibrium is. It means zero net force acting on your object. And so, how do we do that in terms of potential energy? We kind of go back the other way. So we had already found that to get the potential energy, at least the change in it for any conservative force, it is negative the integral between two positions of that force. Now my problem is I know potential energy. I want to find the force associated with it. I know this curve. Tell me about the forces. So to do that, I just come back to the idea that change in potential energy at any point along this curve at any x is equal to the negative of the work done to get the object to that point. But we'll think about if I take a really small step, how much work does it take to change the potential energy by that amount, delta U? Well, in that case, I can say the force is roughly constant for a very small step. And it's just force times distance. I could rearrange that to find the force. Negative delta U over delta X. But then the last step is to say, okay, but in order for this to be 100% correct, I need it to be a very small step. Otherwise, I'm not guaranteed that my force actually is constant. It might be roughly, but the only way I can guarantee that it truly is constant is to consider the limiting case of this. The limit as delta x goes to 0. So, in other words, the force is negative du dx. If I know my potential energy, I can take the derivative of it and then slap on a negative, and that will tell me the force associated with it. You may, if you you take more physics classes after this, you'll see the more general version of this, because this is the 1D version. If you're taking Calc 3, you may have seen the gradient at some point. It's the 3D version of the derivative. So in 3D, this is written F equals negative gradient of U. Just think of that as you need to find the slope in this 3D space instead of along a 1D curve. Okay, so that's kind of abstract. If we come back to the potential energy curve, it's a bit easier to see what I mean by that. So I've copied it down here. So it's negative du dx, so it's something to do with the slope of this curve. but because of that negative, it's actually the opposite or negative of that slope. To explain what I mean by that, it's actually pretty straightforward. If I let a boulder go from right there, which way is it going to roll? To the right or to the left?
Right.
To the right. But what's going to happen to the potential energy? Or alternatively, equivalently, let me ask, what's the slope of the curve at that point? Is it positive or negative?
Negative.
Negative. So the du dx is negative, but the force resulting from it is positive, is to the right. So the slope is negative.
It decreases the potential energy.
Yep. But in terms of the force, that's due to a rightward acting force, something pulling this boulder to the right. And I know it looks like I should say it pulls it down. Remember, this is still representing a 1D motion. This is just kind of giving us a 2D picture of it. We're looking at variations in potential energy, not an actual height. So the system we're looking at, the object is still just moving along the x-axis. But yeah, if we have a negative slope, that's a positive force. And so that's what's going on between x1 and x2, is we've got a positive force value. So I'll just say, I'll plot a little positive point there. The easiest points to talk about, though, are where the slope is 0. In that case, how much force is acting? So like if I've got a ball right here, how much force is acting on it?
Nothing's acting on it.
Yeah, it won't be pulled in any direction. So where the slope is 0, the force is 0. So equilibrium, meaning 0 force, that happens where this potential energy curve is flat, where it has no slope to it. So what other equilibrium points do you see?
X4.
X4, yep. All right, where else?
X3.
X3. All right, any others?
Would you say that X5 is 0 as well?
Yeah, yeah. And what you're noticing there is it's sort of an extended equilibrium. We've got 0 slope for a while. And then even up before X1. Our imaginary boulder would just sit at each of these points if we didn't give it a push. It would just stay there. So I'll put all of that on my force curve. I'm turning this potential energy curve into a force diagram, a force curve. So I know at x3, I'm sorry, at x2 even, the slope is 0, so 0 force there. At x3, it's 0 again. At x4 is 0. And everywhere past x5, it's 0. And then for this little bit before x1, it is 0. Now I just sort of need to connect the dots. So everywhere between, and are y'all seeing my cursor on this view?
Yes.
Okay, great. All right, so everywhere between here and as I'm falling down to the bottom, what can I say about the force? Is it positive or negative? So remember, it's the opposite of the slope between those 2 points.
Sorry, between what 2 points?
Between up here and then down to x2, because I got to connect the dots between those two.
It's positive.
It's positive. The slope is always downward, always negative, and so the force is always pulling the object towards the right. A positive force. So if I try and connect my dots, it might look something like that. The peak would be where the curve is steepest. That'll be my maximum force for that interval. That's what this is right here. Okay, what about between x2 and x3? What kind of force will act there?
Negative.
Yep, because if the ball is rolling up this potential energy curve, the system is moving away from this equilibrium point, it's going to be pulled back towards the equilibrium point, back towards x2, to the left. So everywhere between x2 and x3, the force is negative. It's not quite as dramatic as from x1 to x2. So I might make it a slightly smaller force value. Not that small. Slightly smaller force value, but something like that. All right, what about between x3 and x4?
Positive.
Positive. But again, we're seeing the variations in potential energy, and so the associated slopes are not that dramatic. So I will do a slightly smaller force value there. But yeah, we're just kind of following the trend. So here it was that the slope is positive, and so the force is negative. Here it's that the slope is negative, and so the force is positive, and so on and so forth. And then from x4 to x5,
Negative.
yep, because everywhere in that interval, the slope is positive, but that's going to make or pull the ball back to the left. So the force is negative. All right, so we've taken our potential energy values and recovered forces from those values. As we went through, you probably noticed that those equilibrium points, those flat points, they look a little different at different spots. So just kind of based on your feel of them, which one of those do you think you would classify as a stable equilibrium? Even easier question, maybe. What looks like a really unstable equilibrium without knowing the exact definition of that?
X1 looks to be unstable.
So if you gave it a little kick to the right, you're saying eventually it would start sliding down? That's why it looks unstable?
Yes.
Okay. I think that is a reasonable idea. The one thing I'll argue is I've got a little bit of room before that happens. So I might say once I get kind of towards the edge, I'm heading into maybe unstable, but at kind of these points where it's flat to the left and to the right of the point I'm looking at, it's still staying pretty flat. It's not going to be a sudden dramatic drop off. Is there an even more unstable looking point?
X3.
X3. Because if I wiggled that whatsoever in any direction, it's going to fall off that cliff because it's sitting on just the peak of it. It's very ready to slide off. That is what we classify as an unstable equilibrium or a hill in the potential energy curve. Reason it's unstable is because, say I moved that ball just barely to the right. Which way is it going to be pulled now? To the right or to the left?
Right.
To the right. So even from a very small displacement from equilibrium, it's going to start rolling away from that equilibrium point. And if I displace it just a tiny bit to the left, it'll feel a force to the left. In either case, it's being yanked away from the equilibrium point. So we would classify this as an unstable equilibrium. All right, what looks to be very stable equilibrium points?
X2. X1. Oh,
So x2, I agree, and x1, I'm still going to hold out on that because there's something different about x2 versus x1. You could think of x1 as a very extreme case of stable. It is very stable. I'm not trying to argue that, but it is even more so, and that's why we'll save neutral for that one. But what stands out about x2 that makes it look so stable?
it's just down the hill.
Yeah, and
Like it's the lowest point.
yeah, that is sort of a physical principle you're getting at, is stuff likes to go towards the lowest potential energy. So, reason being, if we tried to move it away from that equilibrium point, gave it a little kick off to the right or to the left, which way is it going to feel a force? So if I kick it to the right just a tiny bit, which way will it be pulled?
To the left.
Back to the left. And if I kick it to the left, it'll be pulled back to the right. In other words, back towards equilibrium. So it's stable because if I displace the object just a little bit away from it, it tends to want to move back towards equilibrium. From calculus, you may recognize this as doing the second derivative test. You're sort of checking concavity in this way. So the valleys are stable. All right, now neutral is sort of like an extreme case of stable, but it's because if I give it a little kick to the left or to the right, it's still going to feel zero force after at least the little kick I give it. So if I displace this ball on the right just a little bit away from x5, it's still going to feel zero force. But now it's moving. If I've got something that's moving but feeling zero force, what's it going to do? It'll just keep moving however it was moving. That's the inertia of the object. It says just keep moving however you were moving if you're not feeling a force. So in these neutral equilibrium points, it's very easy to get something moving and just have it coast indefinitely. And so this thing will just kind of keep on coasting off to the right for as long as it cares to until it runs into some other variation in potential energy. So neutral equilibrium, or equilibria, are the plateaus of potential energy. Because in this case, it's not a question of moving away from or towards equilibrium when you give it a little kick. It just stays in equilibrium. And that would be, for instance, just moving something back and forth on a flat hill. Not much interesting is going on in that case. Also, it looks like I lost my little x4 to x5 over here, so let me put that back in. And this is just saying force alternates between positive and negative for this example. So that's honestly putting maybe too much technicality into something that you can visually see the answers to. So let's kind of do it that way of we'll answer these questions just based on what feels intuitively right and then try and add the justification. So rank these regions according to the size of the force on the object. Where do you think it's going to feel the largest force of these? So tell me the largest possible force.
AB.
AB. What makes you think so?
Because it's the slope is really is like it feels like the greatest. It's really steep.
It's really steep. It's a quick drop off. And if we come back to what we know about like a hill, something's going to be pulled more and more and more down the hill the steeper the hill gets. The most extreme case being a vertical hill, free fall. So, yeah. AB, I would say, is the largest force. All right. And what kind of force is it? Just for us to keep that in the back of our head. Is it positive or negative for that part?
Positive.
Positive, because the object would be pulled to the right if we put it there. All right, what's the next most? And keep in mind we're looking at just sizes of forces, so positive or negative here is not critical, just how big the forces are.
GH.
GH. So let's see, it goes from 1 to 6. Yeah, I'd say that looks pretty steep to me. Oh, I guess it's just got us ranking just these first ones, but let's go ahead. So yeah, I would say GH is next. And what kind of force?
Negative.
Negative. Because an object placed there would be pulled back to the left. So far what we've got is one placed here would be pulled to the right, one placed here would be pulled to the left. All right, what's next?
Would it be EF?
Yeah, sounds good to me. And what kind of force is that?
Positive.
Positive. And CD? I'm sorry, I gave away the answer. CD would be next, because it's the next most shallow. What kind of force would it be?
Negative.
Negative. And then we're down to the zeros. So all these flat parts of the hill. We're going to see the least force there because it'll be zero force in those cases. Those are our equilibrium points. In this case, though, because we sort of have this piecewise thing going on, they're all technically neutral equilibria in this case. So I would say, and then we've got BC, DE, and FG tying for last. All 0 force. So intuitively, we were just looking at slopes. The more complete justification is that force is negative du dx, negative the slope. And the negative just tells us direction. It doesn't tell us size. Let me specify a little more on that. Direction of force is opposite the slope. All right, part B is what is the largest value of mechanical energy, meaning that lid that we can put on this system to specify what parts are accessible to us. What's the largest value that could have to keep the object trapped between A and D? In other words, I've got my ball, maybe it's down at the bottom of this hill. It has some budget of energy to work with, 3 joules, but I want to get it up to a point where it can reach up to here, but only up to there. I don't want it to escape this region. And so I need to set my maximum budget of energy to what in that case?
To 5 joules.
To 5. If I do 2 more joules of work on this system to get it up to 5 joules of total mechanical energy, that's E, then all it can do is oscillate back and forth between those 2 extremes. Those would be my turning points. Because at those points, I run out of kinetic energy. I've intersected my mechanical energy curve with potential energy. In other words, there's nothing left for kinetic at those extremes. So yeah, that is the answer, is 5 joules. Because the ball will stay trapped if my kinetic energy runs out when we get to the endpoints. I've still got some wiggle room on the left-hand side. It still can't even reach A, but if I raised that total energy budget any more, then it would escape on the right-hand side. It would get past D. All right, what about...
So at
Sorry.
5,
Yeah, go ahead.
or at 5 joules, since that's the turning point, it starts oscillating between A and D.
Yep, exactly. Yeah.
Okay.
All right. What about between E and H? What's going to keep it trapped between those points?
Would it also be 5 joules?
Yeah. So if I give the system 5 joules of potential energy between points E and H, those are horizontal distances, then all the system can do is oscillate back and forth. This may be a spring or something like that, just vibrating back and forth between E and H. Because it can't make it past these endpoints, these turning points.
I have a question.
Yeah.
So what happened? Like, would it also work if you dropped it from 6 joules from like A to B, and would that reach the end of H and oscillate back and forth between E
Yes.
and H?
Yep. Assuming there's no friction, because in that case you'd think of sort of like a trap room where the ceiling is gradually lowering on you. But as long as there's nothing like that sapping energy out of the system, then yeah, you're just going to oscillate back and forth between over here and over here.
All right, thank you.
Uh-huh. And that brings up a good point, is say I did give it more than 6 joules even. In that case, it can escape off to the right, presumably to who knows where. It can keep on going off to the right. And we would call that an escape trajectory. You've given it enough energy to get out of this system. That's actually the way we usually talk about planetary orbits. Is it's a bound state. You are stuck between these extremes. You're oscillating between kind of 2 points in space. Those would be your extremes of the orbit. unless you get enough energy through a thruster kick, something like that, to get you out of the energy well and let you escape off to either side. Um, so you're kind of climbing up out of a hole if you're trying to escape a gravitational orbit. Okay. And let's see. Last one. What is the maximum speed of the object under the conditions of part C? So if I'm trapped between E and H, what's the fastest the object can go? How would I go about figuring that out?
Seeing where the potential energy is the least and like is the greatest.
Perfect. Yeah. So I'm going to be going fastest where there's the least potential energy, which is going to be the bottom of this hill, because that leaves the most, or there's the most left over for kinetic energy there. How much kinetic energy is left over?
At the equilibrium point.
So it's anywhere in this range because we'll see that it's the same kinetic energy everywhere in between.
Mm-hmm.
So how much kinetic energy do I have to work with?
Would it be all of it or?
Give me a number, but yes.
Oh, it's 4.
Yeah, because this is like I'm not at like the very bottom of where I could reach. It's not like the sea level of this system. I'm still sort of on a hill, but it's more of a valley. I'm trapped in that region, and so there is still 1 joule of potential energy technically, but 4 joules remaining for kinetic. So that would be my maximum kinetic energy value. And so we'll say kinetic energy is max, where potential energy is minimum. And it equals whatever's left over of my budget at that point. So 5 joules minus 1 joule, or 4 joules. All right, and now I just need to finish out by saying, how fast is this thing going? Well, I guess I must have cut out the mass of this. Let's say this thing has a mass of 2 kilograms. Let's pretend that was in the problem statement. Well, to finish out then, kinetic energy is 1/2 mv squared. And so that maximum speed I just get by solving for Vmax. And that comes out to 2 meters per second. Okay. So to recap, the idea of potential energy curves is really just to turn problems about any sort of system, at least these 1D systems that we've been looking at, like springs, and in next semester we'll be looking at electric charges, but similar ideas apply. We want to turn them back into problems about just gravitational potential energy, because that's the one that I think clicks best for most people. And potential energy curves let us do that. Then the last thing we have to address is we've been saying let's pretend friction doesn't exist, and let's pretend these outside forces don't exist. And obviously they do. So the question is, how does that affect things if we bring them back into the mix? Well, in that case, we have to see where we first threw out the idea of friction. And it would be back here. When we said, as long as there are no non-conservative forces like friction acting, energy is conserved. I did that after this step right here. So this is my still most general statement. It's still the work energy theorem, just written in a kind of more explicit way, saying what's on the left is your deposits or withdrawals of money, your friction, your tension, that kind of thing, stuff that adds and removes energy from the system. What's on the right is the total change in your energy budget for your system. So I'm going to start over from there and see how I need to continue to account for friction and other forces. So this is your external deposits or withdrawals. This is the change in your total money, the total money of the system. You're looking at total mechanical energy. And that money could come in the form of checking or savings. So you could also write this as the change in what's in your checking account plus the change in what's in your savings account. In that case, it's actually not a major modification because we already know how to do calculations of work done by forces. That's what's on the left. It's just force times distance and then the angle between them. So if we've got some force, maybe a rope pulling or someone physically pulling on the object, something like that, F, it's considered a non-conservative force because it can add energy to the block or whatever you're pulling on. But the work done by it is just that force times the distance you pulled over. If it's something trying to add energy to the system, the angle between those two would be 0. You are pulling in the direction it's moving. So this might be the work done by your applied force. And then friction, same deal, except it's always pulling opposite the direction the thing is sliding. And so that would be a cosine 180, meaning a negative force times distance. This is the work done by friction. So now the work energy theorem becomes whatever work is done by an applied force, all the deposits to your system, minus whatever work is done by friction, whatever transfers there are out of your system, with whatever withdrawals. That determines the change in your total mechanical energy, the total money in your system, total money in your accounts. So this is your deposits. This is your withdrawals. And on the right is still your change in net worth. If I expand out the right-hand side and do some rearranging, I can write it like this. I'll just write the whole thing and then explain. All right, so help me interpret this in terms of that money analogy. What is this saying? All right, well, we'll start from the very left. So that's your initial kinetic energy. In terms of the money idea, what is that?
What you start off with?
Yeah, the initial balance of your, let's say, checking account. And then your initial potential energy is your initial balance in your savings account. What are we saying happens between that initial value of those two things and the final value?
That there's a change, so that'll be like your overall, like how much money you have total.
Yeah, so this is like it's like your starting balance of energy. Well, if you want to find your final balance, that could come from redistribution between your checking and savings accounts. You moved money between them. That would be the conserved part, the mechanical energy being conserved. But you may find that actually, if you add up your final balance between checking and savings, you don't get the same number as what you started with. Well, that could just be because you did have some deposits of money and some money taken out. That's all that these other forces do, these non-conservative forces, is they just change the total value of money, total value of energy in your account. And actually, we could even include them as a new type of account, a new energy account. And that's one way you would move forward. That's the way the book tends to do it. I feel like this is easier to get your head around at first, but that's what this asterisk is saying. Instead of looking at it as the work done by friction, we could actually think of it as a new energy account called thermal energy. And what you're saying, as two things rub together, is that you're just putting some of your budget into the thermal account now. That would be that the two objects are heating up as they rub against each other. The block moving on a ramp is heating up on the lower surface, and so is the ramp. It is technically more correct to talk about it that way, but it's for really kind of subtle reasons that are not important at the moment, but more important for like thermodynamics related stuff. But the general idea I'm trying to get at is if you're careful with your accounting, energy just is conserved. You can always find the account it went to and where it came from. It's never that money just suddenly popped into existence. You can track it no matter what. Okay. And this is just kind of putting all of that stuff together. It's just a lot of calculation. With these problems where we do have friction, now this thing in the box is your starting point. For the ones where we didn't have friction, it was the slightly simpler version, k plus u equals k plus u. Friction just adds a couple terms, adds a couple things to the balance sheet, but otherwise doesn't really make things any worse. So we have a spring compressed 5 meters to launch a child on a cart down a 35-meter tall water slide at the bottom. He slides along a rough track, bringing him to rest. How far does he slide along the track before stopping? This would be a nightmare, if not impossible to do with Newton's laws, because all this stuff going on in between. So let's use this work energy idea. Which now you are really truly seeing is just accounting 101. Whatever you start with, plus whatever deposits are made to your account, minus whatever withdrawals are taken out, determines what you end up with. In this case, we actually have two different types of potential energy, though, two different savings accounts. There is both gravitational and elastic. They're high up, and they're sitting on a compressed spring. So we can actually expand this out even more. Kinetic energy is 1/2 mv squared. Potential energy, again, has two types. There is gravitational and elastic, plus deposits minus withdrawals equals your final balance. And if there was more stuff going on, there were explosions, there's chemical energy involved, or nuclear energy. It's just more terms. It's just more stuff to add on the pile, but in principle, not really much worse. All right, so this is your final potential energy, two types. All right, this would be a nightmare to do the algebra for just immediately, so let's see if we can throw out anything. Also, there's several typos in this. This should say to launch, and this should say just before.
The VF, because it would stop at 0 velocity.
Yep,
Or,
perfect. So VF is 0, they come to rest, and so I can throw out this term. What else?
The final potential energy,
Which one?
the gravitational.
Yep, because that is our lowest point. We've used it all up. If we choose that to be the 0 level for height. Okay, what else?
The initial elastic potential energy.
Well, the initial is that compressed spring, so we actually do need to compress it in order to launch them. That's our initial state. But what about the
Would
final
you-
state?
Yeah. Would it be 0?
Yeah, because once the spring launches them, it's relaxed again. Once they're at the bottom of the slide, springs definitely come to a stop, fully relaxed. So here, spring is relaxed. So we've pretty much knocked out the whole right-hand side. On the left-hand side, we know the spring's compressed, so they have initial elastic potential energy. We know they're high up, so they have gravitational potential energy. So we're just down to those other three terms. Can we throw any of
The
those out?
initial kinetic.
Yep, because they start at rest and then are launched. So the spring gets fully compressed, and they're just sitting there, and then it suddenly gives them a push. And we're free to relate any two states, so we can relate before they're ever launched to the final state, or after they're launched if we want. And there is one more for that one. Let's just think about the forces acting on them. So what forces are acting on them as they're launched?
The slide is frictionless.
It is frictionless, so there's no friction up here. There will be some down here, and that means we'll still need to keep that FKD, but we know D is not the entire slide length, it's just this length right here. But yeah, there will be some friction. What other forces are acting on them?
Do you mean like the spring and gravity?
Yeah.
Gravity.
Yeah, so the spring will launch them. We have that spring force, and we've already taken care of it through that elastic potential energy. We have the gravitational force. We've taken care of it through gravitational potential energy. What else do we have?
The normal force.
Yep. So that is a non-conservative force, and it potentially could be this thing. But is it doing any work?
No.
No. How can I tell?
They aren't really in the slide. Or
Yeah, so the normal force is always perpendicular to the direction they're moving. It's just keeping them on the slide. So it's not that non-conservative force doing work. In other words, we looked at every force involved here, and either they're already accounted for in a potential energy term like one of these, or this frictional term. There is nothing that goes here. There's no other tension or some other outside force that is non-conservative and doing work on this system. So I can throw this out, because aside from friction, which has its own special term, no other non-conservative force is doing work in this problem. If they were launched from a spring and someone were pulling them along with a rope, yes, the rope would be the non-conservative force doing work. But in this case, that's not happening. All right, so thankfully we have drastically simplified this. So let's write out what we've still got. Okay, and we are trying to solve for the distance L, so how far they slide once they're in the water at the bottom. And so I'm going to replace this kind of generic D variable, the distance, with that. That's what they want us to say is the distance they slide. So I need to solve for L. The other thing to keep in mind is that thing I mentioned about you could put everything like we did here and then take stuff away, or you could just add in what's relevant. So we started with them high up, so there's gravitational potential energy. We started with a compressed spring, so there's elastic potential energy. We take that energy away with friction. That's really all that's actually going on, and that's all this equation says. So if it makes more sense to you to add terms rather than remove them, feel free to do it that way. All right, so we solve for L. It'll be all this mess over the kinetic friction. What do I know here? What don't I know?
You know the elastic,
Yep.
the K
Mm-hmm.
value.
I know K. I also know X initial. It's compressed 5 meters. I know their mass. That's up there. I know the initial Y. What about FK?
you have to solve for that one.
Yes. And for that, I do need to unfortunately remember Newton's laws for a hot second. So if I look at when they're down here, still got the normal force and their weight. So I can say that's essentially a free body diagram. I can say the net force in the y direction is Fn minus mg equals mass times y acceleration. They're not actually doing anything in the y direction down there, so normal force is equal to mg. And that's necessary because, remember, the kinetic frictional force is coefficient of friction times normal force. I need this to be able to say how large the normal force is. Coefficient of friction times, in this case, the weight. So I'll put that in over here. And I know the coefficient of friction, I know their mass, I know g, so finally I have everything I need. So 200 kilograms, 9.8 for g, initial height of 35 meters. Spring constant is 3.2 times 10 to the 3. Didn't leave myself enough room as usual. So this was pointing over here. Spring is compressed 5 meters. Coefficient of friction is 0.8. Mass is 200 kilograms and 9.8 again. And after tedious calculation, we get 69 meters. Nice. So this is really involved, and I wouldn't really try to make you do it that often other than to see that it's kind of the same process. It's just with more terms and more things you got to decide if they're zero or not. But on an exam, it would be a toned down version of this. So this is probably the worst it would get. Well, that is finally it for Chapter 8. I know we are horribly behind, but believe it or not, I'm actually doing better this year than the last time I did this to keep up with lab. But anyway, we're ready to start on something you've already seen plenty in lab. So I will try and speed along, especially for this first part. But I want to give you maybe a slightly better feel of some of these things than you can get in lab. So we start with the idea of momentum. And the thing to keep in mind for momentum and impulse is it's a third way to talk about motion after force and velocity and work and energy. And it really was, especially when it was first developed, it was just another possibility. People didn't really know, like, one is better than another, or you should use this one when you're doing this, or that one when you're doing that. And it actually was an argument. Newton developed the ideas of momentum and impulse, and Leibniz developed the ideas of work and energy. And this is another thing they fought over, besides calculus, who developed calculus. They would say, I think my way is better for talking about motion. This is the relevant quantity of motion, momentum versus energy, kinetic energy specifically. And what we've realized now is that actually, depending on what's going on, you may need either or both. So they're both important. And so we'll start by talking about it as its own isolated thing. But the further you go in physics, you realize you got to bring up energy, momentum, force, all of them, all the time. So that's why we have to look at 3 different perspectives. Okay, so what momentum is, roughly, is a measure of how hard it is to stop something. So what things make an object harder to stop? If you see it coming towards you and it has this feature, what feature is gonna make you more concerned if it hits you?
Its mass.
Yeah. If it is a giant truck versus a tiny car, I don't want to get hit by either necessarily, but I'd rather get hit by the tiny car. So there's something to the truck having more mass, more inertia. That's going to make it worse if I get hit by it because it's harder to bring the truck to a stop, and the only thing there to do that is my body. All right, but that's not the only thing that would make it bad. What else could make it bad? Say we had identical mass.
The velocity.
Yep. I would rather get hit by the slower car. So, if we have two going at the same velocity, but one has a bigger mass, the bigger mass is worse. If we have same mass, but different velocities, the bigger velocity is worse. So we put that together into a single measure of how bad it would be, how hard it would be to stop this object, and that's momentum. And so it's not just inertia, it's inertia in motion. In order to have momentum, you must be moving. It is mass times velocity. I don't have a good reason for why we use the letter P. I legitimately think we ran out of letters. I looked into it once, and someone said it had to do with the word pillare, like a Latin word that's kind of the same root as like to compel. I don't know if that's actually true or not. So we'll just say it's because we ran out of letters. But anyway, the units are the units of mass, kilograms, times the units of velocity, meters per second. That doesn't get a special name. It just is kilogram meters per second. So, if we come back up to these pictures, we would say, because of its larger mass, the truck has a larger momentum than the car. And over here, because of its larger velocity, the fast car has a larger momentum than the slower one. And momentum is a vector. That's what makes us not like it as much as energy. It has direction, and so we need vector addition to combine momenta. The direction will be the same as whichever way the object's moving. Same as velocity. All right, so momentum is the thing something has. It's the analog to velocity. The other question is, how can we change it? What acts to change something's momentum? Well, it depends on velocity. So we're really asking, what ways, what options do you have to change the velocity of something? How can you accelerate something? So you've got a car speeding towards you with a large momentum. How can you get rid of it? What are your options?
Slowing it down.
By doing what? Applying what?
Opposite force.
Yeah, and so we'll just kind of keep it generic to say some net force. From all forces acting on it, the overall effect of them, that could change the momentum. But for some car speeding towards you, that would likely be it braking, or hitting you is another option, but hopefully it braking. So to stop a car, one option is you could apply a larger force. So if it's got lots of momentum, you'll need more braking force in order to bring the car to a stop. What else could you do if for whatever reason you can't press harder on the brakes? What's your other option?
I mean, it sounds like a bad idea, but like, I guess hit a wall, I guess.
That
I
would
mean,
still be a force acting. So you're right. That is an option. It definitely is, but that's already taken care of by the force option. What other thing could we change? What other physical quantity in order to bring this car to a stop? We could apply that force for...
Reduce its mass.
That is technically another option. We could start cutting pieces off of the car. And if you're talking about rockets, that actually is what we do, is you eject fuel, eject mass. That is a harder option. There's one more that I'm looking for. You can't press the brake harder. Like, I'm saying you're still allowed to press the brake, but you just can't slam down on it. What's your other option to come to a stop? You just press for longer. you hold your foot down wherever it is for a longer amount of time. You maybe can't slam the brakes and it'll take you a greater distance to come to a stop, but you will stop if you just hold the brake down for a longer amount of time. So your other option is time, your delta t. So could apply a larger force or let it act for a longer time. And so if force and time are the relevant quantities, let's turn that into a new thing. We call it impulse. That's what changes the momentum of an object. So loosely, impulse is the effect of a force over time. You could compare it to work, which is the effect of a force over distance, FD. This will be F, now a vector, delta t. So this has a direction, it's the same as the force. And the units of this are Newton seconds, force times time. That does happen to come out to kilogram meters per second, same as momentum. That's kind of hinting at something. So the idea here is stuff has momentum, but you can change it by applying an impulse. The impulse your object feels as a result of some other thing applying it is what changes the momentum the object has. So those are our two relevant quantities for this chapter. I can get the relationship between them just by starting from Newton's second law, the same way we got to the work energy theorem, but now I'll do a slightly different rearrangement. So this is just second law, as usual, but I could also write the acceleration in terms of velocity and time. I can only write it as delta v over delta t instead of the derivatives, though, if it's a constant acceleration resulting from a constant force. So that's something that I have to start with as an assumption, but I'll relax it in just a minute. So if I rearrange this equation, I get net force times delta t equals, it'd be mass times delta v, but since mass is a constant, at least for the moment, we could put it inside of the delta, because it's like putting a constant inside or outside of a derivative. It doesn't change anything. Equals delta mv. So what do we have on the left-hand side of this equation?
Impulse? Or net
Impulse. Yep. Impulse resulting from the net force, or net impulse. And what about on the right-hand side?
Change of momentum.
Yep. Change in momentum. So now those will be our working quantities, net impulse and the change in momentum, and they are related by this. This is just a statement similar to work energy of you give something momentum by exerting an impulse on it. You take away that momentum by an impulse acting in the opposite direction. So the net impulse equals the change in momentum. And that does make it sort of seem like impulse is the cause and the change in momentum is the effect. It actually, there are cases where it makes more sense to go the other way. Say change in momentum is the cause of an impulse. What really matters is just when one happens, the other happens. It's like action and reaction for the third law. There isn't really a causality, it's just when one happens, the other happens. All right, so in symbols, we use J for impulse. That truly is just we're out of letters. I don't think there's a reason for it other than that. Equals change in momentum. And momentum we can write as change in momentum we can write as final momentum minus initial momentum. The impulse momentum theorem is sort of our starting point for this chapter, in the same way that work energy was a starting point for the previous chapters. We will eventually use it to get to the idea of conservation of momentum, similar to conservation of mechanical energy. But we first need to look at that assumption I made of a constant force. That's actually not super useful for us because there are lots of forces that are not constant. So we need to see how we fix that up. If you're getting hit by that car, for instance, you will feel no force, and then suddenly lots of force, and then suddenly no force again. Similar for most impacts. So, say we've got something coming in with an initial velocity, could be a baseball. Has some initial velocity, and therefore some initial momentum to it. During the impact, it will feel some force. I'll put it back out to the right just to make it 1D. It'll feel some force for some amount of time. And as a result of that impulse, the force over time, it will leave with some new velocity, and so some new momentum. And that seems pretty straightforward, but what we're kind of sidestepping, or just looking past real quick, is the impact part. Thinking about the force during that collision. It's not an instant on and then off. Instead, what happens is, before the ball hits, of course, it's not going to feel any force. So we're starting at zero, starting at nothing. But then, the ball is going to start to squish. The reason for that squish is the inertia of each part of the ball. The part that's in direct contact with the bat, it knows it's feeling a force very quickly, and so it will start to change its motion. But the part over on the far right edge, it doesn't know it's been hit yet. It's not going to change its motion, it's going to maintain the leftward motion, even while the left-hand side of the ball is starting to move back to the right. In other words, the ball is going to squish. That makes the force climb and climb and climb, because we're able to keep pressing into the ball as it squishes, and every bit of it catches up and starts to feel that force. So it's actually going to go something more like this, and eventually reach some maximum value. That maximum is going to be roughly when the ball figures out that it's moving, when the entire ball realizes it's feeling a force. From that point on, it'll start decompressing and moving away from the bat, and so that force will drop back off. So this is the actual force over time. And that means, if we look back at this impulse momentum thing, what force are we even talking about? I don't know, because there's lots of force values over this span. Before I get into that more, I want to show you that. Compression, this is for a golf ball, but baseballs, it's similar, just not as dramatic. Golf ball hit at something like 120 miles per hour. Just watch how much it compresses before it starts to move. And actually, we have that sort of inertia too. If you get slapped. Watch how the left side of his face figures out, or I guess it would be his right side, figures out that it's been hit long before the other side does. I think we can even find the frame. Something about like there-ish. One side of his face is having a bad time. The other side still looks pretty happy. So the rate at which that information moves across, this is kind of interesting. It's not really relevant for what we're talking about, but kind of neat, is it's the speed of sound in whatever material. In this case, in his skull, but in other cases, it's the speed of sound in the ball or the bat or whatever's being hit, because that is the rate at which pressure changes are transferred. So however fast the speed of sound is in that object, that's what determines how quickly this force travels through it. But anyway, coming back to the idea of I can't pick out a single force. I could if I looked at a very short time span though. And this will be the last thing we write, but I say, all right, well, for this little short time, this little dt, there is a definitive force associated with that. And so I could calculate the impulse for that little speck of time. And then I could add on the impulse in the next bit of time, and then the next bit, and the next bit. Where am I going with this?
The integral.
Yeah. So if I want to find the overall impulse, the overall effect of this force over time, I just add up the effect of all these little individual forces. But that's going to give me the area under that curve. So for this curve, let me do it in black actually. This area it represents the impulse provided by the ball. The total change in momentum that's going to result is that area. So the impulse is add up all the little bitty impulses from your starting time to your ending time. So in this, my starting time would be, I guess, 0. My ending time is this, or in total, this is some time span, delta t. Okay, we'll stop there, but we're going to come up with a way next time to be able to replace that more complicated force curve with a simpler one. And that'll make the whole rest of this easier to do. All right, well, I will get Chapter 8 homework up if I didn't already. Chapter 9 practice. I'll think about how to space those out as best I can. And I'll be working on grading over the weekend. Ooh, only other thing. We do have our Chapter 8 quiz on Tuesday because we just finished Chapter 8. So just be prepared for that. All right, have a good day, y'all.